Let me give you an example of a multiplicative group. Previously we saw groups like this. We have some set and some operation, and we did a group, let's say dz with operation plus. Okay, now I want to show you a group with a multiplication type of operation. And what we're going to do is take a prime number, prime p, and for a specific example, let's take p as 7. And we're going to take the residues mod 7, mod p, okay? And we'll see how this works. Okay, what are the residues mod 7? 0, 1, 2, 3, 4, 5, and 6. Let's exclude 0. Let's take these residues. Now I claim that this forms a group. This forms a group. Now under what multiplication though? Not normal multiplication, because 6 times 6 is 36. That's outside these numbers. Well, under multiplication mod 7. So I have my set, or let's call it G, my set G, 1, 2, 3, 4, 5, 6, and my operation is going to be multiplication mod 7. And I say this forms a group. Now, to prove that this is a group, we're going to show that it has the properties that every group has. Closure, associativity, 2, associativity, 3, it has identity, and it has 4, has inverse. Every element has an inverse. Okay, well, associativity, I'm going to dispense with it right now with some hand waving. I know that multiplication is associative. Multiplication mod 7 is associative, but I don't need to say any more about it. Okay? So let's look at the other properties. The other properties are what we need to do some work on. Okay, closure. Now to do closure, I can just build a table. This is a small group. G is small. It's only 6 elements, right? So G is only 6 elements, so I can build a closure table or multiplication table. It's actually called a Cayley table. So let's build the Cayley table with multiplication mod 7. 1, 2, 3. Well, I should make it a bit bigger maybe. What do you think? I think so. Let's make it bigger. Cayley table mod 7. Okay, try to make it bigger. 1, 2, 3, 4, 5, 6. Like that. Okay. 1, 2, 3, 4, 5, 6, like so. And mod 7 multiplication is going to be my operation, my group operation. Okay, 1 times 1, mod 7 is 1, so all of this doesn't change. You can see right away that 1 is going to be my identity. See, 1 times 2 is 2, 1 times 3 is 3, and so on. So 1 will be the identity. That's obvious right away from the beginning. Okay, 2 times 2 is 4, 2 times 3 is 6, 2 times 4 is 8. Mod 7, that's 1. Remember, mod 7, remainder on division by 7. 3 times 5 is, 2 times 5 is 10, that's 3. 2 times 6 is 12, that's 5, mod 7. Look carefully. This row is a permutation of this row. Look. 1, 1, 2, 2, 3 goes here, 4 goes there, and 5 goes here, and 6 goes there. This row is a rearrangement or permutation. It's a permutation of the other row. Let's keep going. 3 times 2 is 6, 3 times 3 is 9, mod 7, that's 2. 3 times 4 is 12. Mod 7, that's 5. 3 times 5 is 15. Mod 7, 1. 3 times 6, 18. Mod 7, 4. 14 plus 4 is 18, so it's 4. Again, it's a permutation. Look, 1, 2, 3, 4, 5, 6. I have all the elements just in a different order. Okay, all the elements are there just in a different order. 4 times 2, 8. Mod 7 is 1. 4 times 3 is 12. That's 5. 4 times 4 is 16. Mod 7, that's 2. 4 times 5, 20. Mod 7, that's 6. 4 times 6 is 24. Mod 7, it's 21 plus 3. 1, 2, 3, 4, 5, 6. Again, it works. 5 times 2 is 10. Mod 7, 3. 5 times 3 is 15. That's 1. Mod 7. 5 times 4 is 20. 20 mod 7. 20 mod 7, it's not 20, it's 6. 5 times 5 is 25. Mod 7, that's 4. 5 times 6, 30. Mod 7 must be 2. 6 times 2 is 12. Mod 7, 5. 6 times 3 is 18. Mod 7, that's 4. 6 times 4, 24. Mod 7, that's 3. 6 times 5, 30. Mod 7, that's 2. 6 times 6, 36. Mod 7, that's 1. Now look at this. This is 1, 2, 3, 4, 5, 6. The last one, I never noticed this before. The last one is in opposite order. 1, 2, 3, 4, 5, 6. Again, permutation. Permutation. Interesting permutation. Interesting point, very interesting point. We'll come back to this. We'll prove in the next video that it's always true for this kind of group. Alright, so it's obviously closed. Any two elements A and B in G, if I multiply them mod 7, it's also an element of G. I don't have anything in this table that is outside G. All entries in the table are in G, so it's closed. G is closed. Okay, so closure is true. Okay, 3, identity. It's obvious that the number 1 is the identity because when I multiply by 1, nothing changes. So 1 is the identity and 1 is in G. Okay, now 4. This is non-trivial. This one, the inverses. Let's take all the elements A in G. Okay, 1, 2, 3, 4, 5, 6. We'll make a little table. And we're going to find their inverses. A bar in G. A bar, where, of course, A bar is going to be 1. So A bar is the inverse. So let's use this idea. A times A bar mod 7 must be 1. So that gives us a clue. Look where all the 1s are in the table. 1. Okay, 1, 1, 1, 1, 1, and 1. Alright. What's the inverse of 1? Well, I multiply 1 by 1, I get 1. So the inverse of 1 must be 1. What about 2? What's the inverse of 2? Well, look where the 1 is. Here. Okay. Here. Inverse of 2 here. 2 times 4. 2 times 4 is 1. So 2 times 4 is 1. 4 is the inverse of 2. Next, 3. Where's the 1? The 1 is here. 3 times 5 is 1. So the inverse of 3 must be 5. Next, 4. 4 times what? 4 times 2 gives me 1. So the inverse of 4 must be 2. Inverse of 2 is 4. Inverse of 4 is 2. What's about 5? 5 times 3 gives me 1. That's here. Finally, 6. What about 6? What's the inverse of 6? 6 times 6 is 1. 6 is self-inverse, just like 1. It's very interesting. Very interesting. Look at this. 1 permutes them in the original order, doesn't permute them at all actually, and 6, which is self-inverse like 1, reverses them. Very interesting, yeah. It's food for more thought. Okay, next we're going to do the, well, we did the inverses, but I want to show you something more that we can do with this. So we have all of our properties. We have shown that it's a group. Everything has a unique inverse. It is a group. But I want to show you something else. Let's take these boxes. 1, 2, 3, 4, 5, and 6. Okay. These are my inverse boxes. If a number has an inverse of 2, or let's say, then I put that number in box 2. And here are my original elements of G. Now, what's the inverse of 1? Well, that goes into this box. What about 2? Look here. Inverse of 2 is 4. So I put 2 into box 4. Okay. 3 goes into box 5. See? Inverse of 3 is 5. 4 goes into box 2. 5 goes into box 3. And 6 goes into box 6. So if this is A inverse, and I organize them into boxes. So you see, even the inverses is some kind of permutation of the original elements. That's very interesting. And this gives you a hint. This gives a hint on how to apply Dirichlet's pigeonhole principle to this kind of problem. And that's what we're going to do in the next video. We're going to prove it. Okay, we're going to prove it in the next video. We're going to prove that this works. This kind of group, residue set with mod P multiplication is always a group. Okay, and with P prime. Okay, P prime. That's what we're going to prove the next time. We're going to use arguments that are similar to this. Okay, we're going to go a little bit beyond this proof here, just proving these things. We're going to prove that in fact every row of this table is a permutation, and we're going to use Dirichlet style arguments to do that. Okay, so if you like that, if you want to see it, click like on this vid, subscribe, send me a message, leave a comment. If you're interested in other topics, you want me to do one, leave a comment and tell me, and I'll see what I can do.